Hi friends, in the last video I told you how to calculate the potential energy when you have a system of charges. Now say you have these two charges. You know that the potential energy of this system is Q1 Q2 by 4 pi epsilon naught R12, where R12 is the distance between these two charges. Now if these two charges are placed in an external electric field, you just have to take the effect of this external electric field into consideration. Here the potential energy varies. Now what I'll do, I'll calculate the potential V1 at the point A due to this electric field only, which is VR1, and multiply it with the charge Q1. Similarly, I'll multiply the charge Q2 with the potential VR2 at this point B due to this electric field, external electric field. Now, if I add these three terms, this gives me the net potential energy of this system after taking the external electric field into consideration. You will better understand this after I explain you an example. Say this: you have two charges, 7 microcoulomb and minus 2 microcoulomb, placed at 9, 0 and minus 9, 0. I mean, the distance from the origin is 9 centimeters. You have an electric field which varies as A by R square, where A is the constant. It's given there. Now, I want to calculate the potential energy of this system. First, I'll multiply the first charge, 7 microcoulomb, with the potential at this point A due to this external electric field. It will be A by 0.09 because this is in centimeters, and if electric field varies in this way, then this will be the potential at that point. And similarly, I'll multiply this minus 2 microcoulomb charge with the potential there, which is also A by 0.09, and I'll add the potential energy due to the interaction between these two charges, which is minus 2 into 7 into 10 power minus 12 by 4 pi epsilon naught into 0.18, because that's in centimeters, right? Just calculate it. You will get it something like 49.3 joules. That's it. And there is one more point I need to discuss. If you have an electric field in this way, what if you have a dipole here? If you have a dipole here and say this angle is theta. Now this is plus q and this is minus q. This is the electric field. Well, the dipole here rotates, right? Even here the potential energy changes. It varies like the change in potential energy is P into cos theta naught minus cos theta 1, where theta 1 is the final angle and theta naught is the initial angle, and P is not the potential energy here. P is the dipole moment and E is the electric field. This will give you the change in potential energy when dipole is placed in the electric field. And note that this will take care of the sign as well, because if initial theta naught is greater than theta 1, as you know, for cosine, the smaller the angle, bigger the cosine. So if theta naught is greater, you will get the final energy to be negative, which means that you don't have to do work, you will get work. And let's move on to our next topic. Now I'll discuss with you some important properties of conductors. If you have a conductor here, solid metallic conductor, electric field inside the conductor is 0, whatever may be the outside environment. If you place this conductor in a electric field outside, what happens is the charges inside the conductor get redistributed such that the net electric field inside the conductor finally becomes 0. Say if you have electric field in this direction, then what happens? All the negative charges come here, some positive charges come here, so that the normal external electric field and the electric field due to these redistributed charges get cancelled, and finally there is no electric field inside a conductor. And the next property is electric field at surface of the charged conductor must be normal to surface at every point. Well, let me prove this. You have this surface of the conductor. If this was not true, I mean, if you had the electric field something like this, it means that there is a component of electric field in this direction, parallel to the surface or on the surface. And this should not happen, because if this happens, the charges on the surface can move, but that shouldn't happen in a static situation. The potential at all the points on the surface of a conductor should be constant, which means that there is no electric field component on the surface. So this is false, and it means that electric field always is parallel to the normal vector of the area. Now let me move on to the next property. Interior of a conductor can have no excess charge. See, let me tell you, if you have a conductor here, if there was some excess charge here, say, then I can form a Gaussian surface here and say that there is some electric field here. But this shouldn't happen, right? Because as I said, in the first property, there is no electric field inside a conductor. So there can be no excess charge inside a conductor. Electrostatic potential is constant throughout the volume of the conductor, and if it was not constant, it violates the first, second and third laws. Actually these laws appear to be different, but all these laws go parallel. One law follows the other. So even this is the same thing. If the potential was not constant on the surface, it means that charges can move. It means that there can be a electric field component, which means that you're violating the other laws. So hope everything is clear till now. Let me share the next law or next property. See, this is something interesting. The electrostatic field or the electric field near the surface of a conductor is sigma by epsilon naught in this normal direction. Well, sigma is the surface charge density, you know that, and epsilon naught is the permittivity of free space. Now this appears similar to something we have dealt before. Let me remember it. In the video of applications of Gauss law, I said that take an infinite sheet here, and I took a Gaussian surface here like this, and said that the electric field here is sigma by 2 epsilon naught. In this is in the video where I discussed applications of Gauss law. I said that this is an infinite sheet, and here I am saying that the electric field near the surface of conductor is sigma by epsilon naught. Now what is the difference? Observe this. In the applications of Gauss law, here I took an infinite sheet. This is a sheet, but here I am telling that this is a metal conductor. In other terms, I should say that a sheet has no thickness, zero thickness. I mean, it has only one surface. Here there is the surface which holds the charges, and this surface is giving this field lines in this direction as well as these directions. So it is managing two surfaces at a time. So through each surface you are getting the electric field of this thing here. But whereas in the case of conductor has some thickness. You can call it a plate. It has two sides. So what happens here is, if this is the conductor, here is your surface, say, then the electric field here given is given by the charges on this surface only. Well, whereas the electric field given in this direction, it is given by the charges on this surface. Here there are two surfaces which are taking care of the situation, I should say. So I hope you understood the difference between these two. If not, feel free to watch the two videos again and compare, because let me tell you friends, clarity precedes mastery. This is the line I wrote on the first page of my notes in my childhood. Hope it will be helpful for you. Hope it will be helpful for you also. And let me go to the next law or property. I like this one. This is my favorite because it comes very handy in practical situations. Suppose you have a conductor here, some random shape, and you have a cavity inside it. And if there are no charges inside the cavity, I can directly say that electric field inside the cavity is zero. Whatever may be the shape of the conductor, whatever may be the size or charge on the conductor, or whatever environment in which it is placed, it doesn't matter. The electric field inside will be zero. Using this thing, you can create an environment which is completely isolated, or which is electrically isolated from the rest of the world. Dielectrics are nothing but some non-conducting substances with I should say no charges inside them, or even if some charges are there, you can say they are negligible. When dielectrics are placed in an external electric field, they react in different way depending on whether they are made of polar molecules or non-polar molecules. Let me explain you both of them. Say if this is your dielectric, there are many molecules inside it, which can be taken as dipoles. I say this is the positive end, this is the negative end, this is the positive end, this is the negative end. Say these molecules have some permanent dipole because they are made up of some polar molecules like HCl or H2O, anything. Even though they are polar, they are just randomly arranged before placing in a external dielectric, external field, before placing in an external field. Now, if placed in an external field, what happens is all the dipoles get arranged in a particular way. I mean, this way. Here comes the negative, here positive. Here comes the negative, here comes the positive. So, all these dipoles together add up to form to give a net dipole. Now, what if you have a material made of non-polar molecules like H2, Cl2 and any stuff? Say you have a molecule here. Initially the centers of positive charges and negative charges were the same, but now when placed in an external electric field, the positive charges and negative charges get separated by a little distance. So you can say that they act as dipole, or you can say that the dipole is induced in them. When placed in an external electric field, the dipoles get induced and give you this arrangement. Similar arrangement actually. Now I'll better show you some other picture which gives a nice idea. Observe here, the positive charge of one dipole is sitting next to the negative charge of another dipole. Everywhere it is the same. So what happens here is the net charge here is 0, here, everywhere. So the net charge is nullified inside all this dielectric, except at the ends you can say that there is a positive charge accumulated, and at this end you have a negative charge accumulated. And these are the charges that are responsible to create an electric field which reduces the effect of external electric field. And this is something similar to what we saw in the case of conductors, but just note that in conductors there were free charges, but here those charges which are accumulated on these surfaces, they are bound charges, and even the electric field is not completely nullified, it is just reduced, I should say. But to what extent it is reduced, it depends on the material which you are using as a dielectric. And there is something else I should say, it is polarization, which is nothing but epsilon naught chi and chi e, and this is the susceptibility, and it is also the characteristic of the medium. And you have electric field, and this is only for linear dielectrics. Now you get another question, what are linear dielectrics? Well, if the net induced dipole in this dielectric is parallel to the electric field direction, then you can say that they are linear dielectrics, otherwise not. Now this is what is the polarization. This formula is only for linear dielectrics. And that's it for today. Hope everything is clear. In the next video I'll start capacitors. Bye, have a good day.